Hello there, Mr. Sutton here, bringing you the BC Calculus 7.3 Extra Practice number 2 solutions on transforming Maclaurin series. For this problem, we want the first three non-zero terms in general term of the Maclaurin series for this function. So let's start with the Maclaurin series for just cosine of x. That's going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and then they want the general term. So that's going to be negative 1 to the n, and we're going to have, let's see here, an x to the 2n over 2n quantity factorial, something like that. All right, so now for this transformation, we just have to replace x with x over 2. So going from left to right with these terms, 1 is just going to be 1. Nowhere to actually plug an x in there. But this x squared over 2 factorial, well, now we're squaring x and 2 here. So we're still going to have an x squared on top, but we're going to have a 2 squared as well that we're just going to shove in the denominator there next to the 2 factorial. And then for this next one, well, now we have x to the fourth over 2 to the fourth, still have a 4 factorial down there. And in general, we have negative 1 to the n. Up here, we have an x to the 2n. Now downstairs, we have a 2 to the 2n to go with the 2n factorial. And that's it. For this problem, they want us to use a series to evaluate the limit as x approaches 0 of this craziness. So I'm going to start by writing the series for just e to the x, and we're just going to build this off of that. So e to the x, that's going to equal 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and then so on and so forth. We'll just take this out to 4 places so far, 4 terms. So next thing I'm going to do is I'm going to do e to the negative x squared. So that's just going to be all of this stuff, but we're going to replace x with negative x squared. So the 1 is still going to be a 1. This x is now a negative x squared. Here I have a negative x squared being squared, so that comes out to positive x to the fourth over 2 factorial. Here I have a negative x squared being cubed, so that ends up being still, this is actually going to come out to a negative. But then we're going to have an x to the 6th power over 3 factorial. Okay, let's keep going now. We also have to subtract 1 from everything. So e to the negative x squared minus 1 is essentially going to be all of this stuff, except this 1 in the beginning is going to cancel out. So we have negative x squared plus x to the fourth over 2 factorial and all the rest of those. And at this point, I've got enough. I'm just going to go straight to the limit now as x approaches 0. Of all this stuff. In order to do this, I'm really taking the limit of all of this stuff right here divided by x squared. So this is going to be the limit of, this is actually going to be a negative 1 if I divide that by x squared. And this next term, this is going to be x squared over 2 factorial, followed by minus x to the fourth over 3 factorial, and so on and so forth. Now I can actually evaluate this limit as x approaches 0. I don't have a 0 in the denominator anymore. So if I just plug 0 straight up into all the x's, all these x terms here, everything after negative 1 is actually just going to get zeroed out. So all we're going to be left with for this is just negative 1. For this problem, we're being asked to use a series to evaluate this limit. Now you might know just off the top of your head that this limit has a value of 1. It's kind of one of those that you might have been asked to memorize back in the day. You might also be able to do this using L'Hopital's rule. In fact, this is a good candidate for L'Hopital's. But we want to do this using a series because they said so. So a good place to start would be to write out the Maclaurin series for sine of x. So this is going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on and so forth using this pattern. So next, let me take the limit of all of this stuff divided by x. So if I divide x by everything here, I'm going to end up with a 1 for this first term. And then this next term, this is going to be minus x squared over 3 factorial plus x to the fourth over 5 factorial, and so on and so forth. Now, the benefit of what we just did here is, initially we would get 0 over 0, which is bad news. But if we take the limit now as x approaches 0, well, look at that. This first term, we're not getting 0 in the denominator anymore. In fact, we're only getting zeros in the numerators now, which means that if you plug 0 in to take this limit, you're going to end up zeroing out everything except this very first term. So then our limit is going to be 1. For this problem, they want us to find the Taylor polynomial of order 4 at 0, so basically fourth order Maclaurin polynomial for f of x equals e to the negative x, and then use it to approximate f of 0.25. So let's start by getting the polynomial itself. To do that, I have to first start with just the Maclaurin polynomial for e to the x, which is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And I'm going to go one more because they wanted a fourth order polynomial for this other expression. So let me just go one more so I have enough terms. That's going to be plus x to the fourth over 4 factorial. And we could keep going. Now at this point, I'm going to approximate f of x by replacing it with a fourth order polynomial. And actually approximating e to the negative x here. So to make this transformation, I'm just going to plug negative x in for all the x's in my e to the x polynomial. So we're going to have 1, and then this x is replaced by minus x. X squared, we're plugging in negative x there, but squaring that keeps it to be a positive. So this is still going to be positive x squared over 2 factorial. Next, if I plug in negative x in for this x, raising it to the third makes this whole fraction negative. So we have minus x cubed over 3 factorial. And then all the even powers just stay positive. They're going to keep themselves positive. So that's going to be plus x to the fourth over 4 factorial. And no dot, dot, dot. Because this is a fourth order polynomial, that means that we are done when we get to the fourth derivative term. Okay, so at this point, we're going to approximate f of 0.25. Now, this is a calculator problem, so I'm going to do all that on the calculator. One thing I'm going to do to make my life a little easier so I don't have to keep writing 0.25 is I'm going to go to my y equals, clear out whatever's in there, and I'm actually going to write this polynomial in there. So we've got 1 minus x plus, let me do fancy fraction, and I'll have an x squared over 2 factorial, which is just 2. I'm not going to bother with the factorial yet, minus fancy fraction. We've got x cubed over 3, and to get factorial, you go to math, and then, let's see, go over to probability, and it's option 4. So that's kind of a pain to enter, but there we are. And then finally, we have plus fancy fraction x to the fourth. And now we've got 4 factorial. So let me go to my math menu, option 4. There we go. All right, so quit out of there now. And then let me just do alpha traced and pull up y1. And now I'm just going to plug 0.25 into that, just like a regular function. Press enter. Take it out to 3 decimals. This is going to be about 0.779 if we round that off. For this one, they want to know the coefficient of x to the fifth in the Maclaurin series generated by sine of 3x. So the long way to do this would be to take 5 derivatives of this thing and then write that, basically plug 0 into that thing over, I guess it would be 5 factorial. Quicker way is if you just know the Maclaurin series for sine of x and we do a simple transformation on that. So Maclaurin sine of x, that's going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And we could keep going, but this x to the fifth term is really what we're interested in. So to get sine of 3x, we just replace all the x's with 3x's. So this is 3x, which we don't really care about any of these earlier ones, but we'll do it. We've got 3x. This is going to be 27x cubed over 3 factorial. And then this one, now we have 3 to the fifth power. You might know that that's 243. So 243x to the fifth over 5 factorial. So now the x to the fifth coefficient is going to be the 253 over the 5 factorial. Well, what is 5 factorial? 4 factorial I know is 24. So multiplying that by 5, we have 120. So then you could just write 243 over 120, or if you wanted to, these both can be reduced by 3. 243 over 3 is going to be 81. 120 over 3 is going to be 40, and it doesn't really get any better than 81 over 40. On this free response problem, we have this f of t function, 2 over 1 minus t squared, and big G of x is this integral function, the integral of f, basically. So our first task here is to find the first 4 terms in general term for a Maclaurin series generated by f. So you could start taking derivatives of this thing, but that's way more work than you need to do. You might notice, if you look carefully, this is in geometric series form. you have some constant over 1 minus something with a t in it. So this is definitely a geometric pattern. Our a1 value on this one, our initial term, is going to be 2. And then the r is going to be whatever you're subtracting from 1 down here. So that's going to be t squared. So just writing a geometric series, we can write that this is equal to 2 plus, well, now we have to keep multiplying by t squared to get the subsequent terms. So this is going to be 2t squared plus 2t to the 4th. And they wanted first 4 terms in general terms. So we've got another one, a plus 2t to the 6th. And then finally, we have a 2, and we have a t to the 2n. And that'll be for like a starting value of n equals 0 then. Yep, that would work. So yeah, 2t to the 2n. For this part of the problem, they want us to find the first 4 non-zero terms in Maclaurin series for g. So g is based off of f of t, which we saw back in part A was 2 plus 2t squared and all the rest of these. So the g function, which is essentially the integral of that from 0 to x, is pretty much going to be the antiderivative of all this stuff with x plugged in. And we don't really have to worry about this 0 lower limit. Because if you do the antiderivative of all this stuff with an x minus the antiderivative of all this stuff with a 0 plugged in, since all of these terms are going to have t's that go with them when you take the antiderivative, plugging in 0 is going to get rid of all of those. So we can just go straight to antiderivative with x. So that's going to be 2x, and then using the reverse power rule everywhere here, this bumps up to a 3. Dividing by that, we have 2/3 x cubed. Plus, this is going to be, let's see, this is a 5 exponent, so this is 2/5 t, or x to the 5th power. And then this next one, this bumps up to a 7, so this is 2/7 x to the 7th. And over here, this is going to bump up to a 2n plus 1. So we have 2 over 2n plus 1 times x to the 2n plus 1. And that'll be it. For this problem, they want us to write the first 3 non-zero terms in general term of the Taylor series generated by e to the x over 2 at x equals 0. So basically, Maclaurin series at this function. We'll start with Maclaurin series for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and just generally x to the n over n factorial. Now they just want the first 3 non-zero terms in general term. So if I'm doing e to the x over 2, basically replacing all the x's in the e series with x over 2. So we end up with, well, we're still going to have 1 for that first term. There's nowhere to plug in an x. This next term is now x over 2. After that, we have x over 2 being squared. So that's an x squared in the numerator. We have a 2 squared moving down to the denominator, and 2 factorial is still there. And we would do pretty much the same thing with everything else. Moving to the general term then, we have an x to the n over a 2 to the n, still have an n factorial down there. For this part of the problem, they want the first 3 non-zero terms in general term of a power series for this function here. So our starting point is again the e to the x Maclaurin series. And just kind of going back to part A of this problem, here is our Maclaurin series for e to the x, 1 plus all that stuff. So then, fast forwarding here, I can really just start with e to the x minus 1. It's basically going to be all that stuff we had, but getting rid of that 1 in the beginning. So e to the x minus 1 then is just going to start with x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial eventually. So we just need to divide all of that by x now. So that's just going to be 1 plus x over 2 factorial plus x squared over 3 factorial plus finally this is just going to be x to the n minus 1 over n factorial. And then that one's done. For this last part of the problem, for the function g in part B, which was this function right here, g of x equals e to the x minus 1 over x, they want us to find g prime of 1 and use it to show that this equation is true. Okay, well, let's find g prime of 1. So let's see here. If I take the derivative of this, that's going to require the use of the quotient rule. So let me set up my box and ribbon. I've got my numerator, e to the x minus 1, denominator is x, and the derivatives of these are going to be e to the x, because that 1 is a constant, it's just gone, and 1. Now, if x equals 1, which I need to do g prime of 1, then I have the following in my box. We've got e to the 1 minus 1. We have just 1 instead of x. Down here we have just e to the 1, or just e, and 1 is a constant, so that doesn't change. Multiplying it out with the ribbon now to put it back together, we're going to end up with e minus e minus 1, so that's actually going to be minus e plus 1. And then down below we have 1 squared. So these e's are canceling. We just have 1 over 1, which is just 1. Okay, so we're going to take another look now at this series. So the crucial part of this is there's also a series version of g. If we look back on the last problem, so right here, back on part B, we notice that the general term of the series version of g of x was this x to the n minus 1 over n factorial. So I'm just going to write that over here. So as a series, g of x equals the summation from 1 to infinity of that general term there. Let's take a look at what g prime of 1 in series form looks like. Because if we've already taken g prime in function form and gotten 1, well, maybe taking g prime in series form and plugging in 1 will help us set up this equation that we were talking about. So the derivative of just this general term, since n is a constant, we're going to use the power rule. So this is going to be n minus 1 in a parentheses times x to the n minus 2 all over n factorial. That's the summand, the expression. But we need to set up this summation part of it as well. Now, the tricky part about this right here is that if you keep n equals 1 as your initial term, look at what's going to happen here. You're going to have x to the n minus 2, which is it's actually going to give you 1 minus 2. You're going to have a negative exponent up here. And then this is no longer going to be a polynomial. In fact, this is supposed to be valid for any x values. If you were to plug in 0, though, and you had this negative exponent, well, now that's going to go down to the denominator and be undefined. So in order to make this totally legal, what we're going to have to do is this n equals 1, we're going to have to turn that into an n equals 2 to get my first term. So then my first term is going to end up being, let's see here, this would be 1 times x to the 0 all over n 2 factorial. So that'd be basically 1 over 2. All right, so now we need to take 1 and plug it into all this. So if I plug in 1 for x, that's just going to be n minus 1 times 1 to the n minus 2 over n factorial. Well, what is 1 to the anything? It's just 1. So we can rewrite this as n minus 1 over n factorial. Notice I'm keeping this n equals 2 around here. And this is about as simplified as it's going to get. Now, we still haven't shown anything about n over n plus 1 factorial. And here's where we get a little bit tricksy again. So one thing that I can do, now that I've gotten rid of this n minus 2 that was causing me trouble earlier, if I wanted to, I could change this back to n equals 1. If I were to do that, I couldn't keep the same stuff in my summand anymore. Because if you're starting with a value of 2, and now you want to start with a value of 1, but you still want to get 2 factorial in your denominator, you can't write n factorial anymore. You have to write n plus 1 factorial. Up here, initially we were going to get 2 minus 1, which was just 1. But if I'm not going to be getting that anymore, if I'm going to be plugging in 1 as my initial n value, well, now I'm just going to have to write n up here. So basically, you're going to add 1 to n if you shift this back to n equals 1 down here. So this becomes an n over an n plus 1. It's essentially a transformation of sorts, a little bit of a shift of a summation. So totally legal to do that. If you take a look at what we're getting, initially this one would have given us 1 over 2 factorial. This one now gives us 1 over 2 factorial. So totally legal what we just did. But hold on a second, because here's the punchline. All of this stuff was g prime of 1. All of this stuff up here is g prime of 1. Well, if g prime of 1 up here we set equals 1, and g prime of 1 equals this stuff, that means this stuff must also equal 1, just the transitive property. So we've proven what we set out to prove here.